Okay, so today we're diving into a fascinating area of particle physics. You've sent over some research on something called jet substructure. Sounds intense. Basically, you're curious about how scientists use these jets to hunt for evidence of completely new particles, right?
Yeah, you've got it. It's like we're doing detective work, but at the tiniest level imaginable.
We're talking about the absolute smallest building blocks of the universe here.
Exactly. And to understand those, we need to get into this thing called quantum chromodynamics. QCD for short. It's like the rule book for how these tiny particles interact.
Okay, QCD. So this governs those even tinier particles, quarks and gluons, that make up the protons and neutrons we all know.
You got it. See, those quarks and gluons, they're held together by the strong force, which is what QCD describes.
Okay, I'm with you so far, but how do we even study these particles? They're way too small to see.
Right. We need some serious tools, and that's where particle accelerators come in, like the Large Hadron Collider, the LHC. They smash protons together at crazy high energies.
Smashing protons. So does that create more quarks and gluons?
It does. But it's not a clean break. Think of it like, you know those crash tests, dummies? It's like smashing two of them together at the speed of light and then trying to figure out what each piece was originally.
That sounds incredibly chaotic. I can't even imagine trying to make sense of that.
It's definitely complex. That's where theoretical physics comes in to help us understand the data, things like perturbation theory or factorization.
Perturbation.
Factorization. Those sound intense. They are, but they basically help us break down those incredibly complicated interactions into smaller pieces that we can understand. But even then, we have to be careful.
Careful of what?
Well, when you're dealing with particles on such a tiny scale, some values in our equations can blow up to infinity, which obviously doesn't make sense in the real world.
So it's like our math is trying to tell us something's infinitely big in a world that's supposed to be infinitely small.
Exactly. So to avoid those problems, we use this idea called IRC safety. It makes sure our calculations stay grounded in reality.
Okay, IRC safety. Keeping things in check. So we've got these super chaotic collisions, but we've got some tools to help us make sense of them. But where did these jets come into play?
Ah, yes. Jets are key. Imagine a narrow cone of particles all traveling in roughly the same direction. That's your jet.
So instead of looking at each individual particle, we're grouping them into these jets.
Exactly. It helps us see the bigger picture. But figuring out what constitutes a jet, that's where jet algorithms come in.
Jet algorithms. So they define the boundaries of those particle cones.
You got it. They give us a consistent way to organize all that data based on things like a particle's momentum and direction.
So there are different ways to define these jets.
There are, actually. There are cone algorithms and sequential recombination algorithms. Each has its own advantages and disadvantages.
It sounds like physicists are always trying to improve these algorithms.
For sure. One popular choice is the anti-Knight algorithm. It's really good at dealing with the messiness of these particle collisions.
The anti-Knight algorithm.
Yeah.
Why is that one so good?
It tends to produce these nicely shaped, well-defined jets, which makes it easier to analyze them later on. It's like if you're a detective, you want your evidence laid out neatly, right?
That makes sense. But I'm guessing actually measuring these jets is no easy task.
Not at all. We're talking about giant detectors. And we're not even measuring the particles directly, but the energy they deposit. It's a huge computational challenge.
Wow, I bet. Okay, so we've got these jets. We've managed to measure them. What's next?
This is where things get really interesting. We move on to jet substructure, where we analyze the internal structure of these jets to see what they can tell us about how they formed in the first place, like what kind of particle created this jet. So, ready to dive into this jet substructure, it's all about those unique patterns, those fingerprints that different particles leave behind when they decay.
Like analyzing the splatter pattern at a crime scene, but on a much, much smaller scale.
Exactly. And one of the first things we look at is the jet's mass.
Jet mass. That seems pretty straightforward. But how do you even measure the mass of something that's constantly moving and changing, made up of all these tiny particles?
It's definitely tricky. It's more like, imagine trying to figure out the total weight of a flock of birds in flight. You can't just weigh each bird individually, right?
Yeah.
You have to consider their movement, how they're all interacting.
Okay, I see the analogy. It's about the collective energy and momentum of all those particles within the jet.
Right. And what's really useful is something called the jet mass distribution. It's like a probability map.
A probability map. Break that down for me.
It tells us the likelihood of finding a jet with a particular mass. So if we see a sharp peak in that distribution, it could mean there's a specific particle decay happening there.
Ah, okay. So a peak could mean we've found evidence of that heavy particle decaying into two quarks.
Exactly. Different particles, different masses. So we're looking for those bumps, those peaks in the distribution that line up with what we know, or maybe even hint at something completely new.
That's amazing. But I imagine those distributions can be pretty messy, especially with those softer particles we talked about, the ones that make things less clear-cut.
You're right, those soft particles can definitely muddy the waters, which is why we use those grooming techniques to clean things up.
Right, like noise-canceling headphones for particle physics.
Huh. Exactly. But it's a balancing act. Too much grooming, and you might lose important information. Too little, and the signal gets lost in the noise.
Finding that sweet spot is crucial. But how do you know if a grooming technique is actually working well? It's not like you can just ask the jet where it came from.
Good point. We need a way to evaluate these techniques objectively, and that's where the ROC curve comes in.
ROC curve. Now, I feel like I should know what that is.
It stands for Receiver Operating Characteristic, but don't worry about the name. Just think of it like this. It's a graph that shows us how good a particular technique is at its job.
So if our jet identification methods are like detectives, the ROC curve tells us if they're any good at solving cases.
Exactly. It shows us the trade-off between correct identifications and false positives. We want a method that gives us a lot of hits without too many false alarms.
Makes sense. Now, we also touched on trimming and pruning earlier. Are those also used to identify those two-pronged jets?
They are, but in a different way. Think of it like this. Imagine you have a bunch of evidence boxes. Trimming gets rid of the empty boxes, and pruning tosses out the ones full of useless stuff.
So they help us focus on the most important parts of the jet, the real clues, so to speak.
Exactly. And we can even combine them with other techniques, like that MMDT you were curious about earlier.
The MMDT. That one definitely sounds like something out of a spy movie. What's so special about it?
It's designed to specifically identify those two-pronged jets, even when they're coming from boosted objects, which can be tricky.
Boosted objects being?
Basically, particles moving ridiculously fast, close to the speed of light. When they decay, everything gets really, really close together.
Like a firework exploding at warp speed. Things get blurry.
Exactly. That's why we need the MMDT. It helps us see those two prongs, even when they're blurred together.
So it's like a superpowered magnifying glass for particle physics.
You could say that. It analyzes the jet structure, looking for those specific splittings that tell us, hey, this might be a two-pronged jet from a heavy particle.
And it makes sure those splittings are legit, not just random fluctuations.
Exactly. But the MMDT isn't the only tool we have. There's also soft drop, which is similar but gives us more control over how we handle those softer particles.
So like having a dimmer switch on our particle filter.
Yeah, that's a good way to put it. We can fine-tune how aggressively we clean up the data, but there's even more to jet substructure than just identifying two-pronged jets.
So we've got the MMDT, we've got soft drop. What other tools are in our jet substructure toolkit?
Well, besides looking for those two-pronged jets, remember those shape variables we talked about? They give us a whole other way to analyze these jets.
Right, like analyzing the shape of a footprint to figure out who left it.
Exactly. One important one is called N-subjettiness. Basically, it measures how well a jet's energy fits into a certain number of subjets.
So for a two-pronged jet, we'd want a low two-subjettiness because the energy is concentrated in those two prongs.
Exactly. It's like fitting a two-pronged plug into a two-prong outlet. Perfect match. But if you try to force a three-pronged plug in there, it's not going to work as well. That's high N-subjettiness.
So N-subjettiness helps us see how two-pronged a jet really is, even if it's not perfectly clear-cut.
Precisely. And there are even more specialized shape variables like energy correlation functions or ECFs that give us an even more detailed picture of the jet's shape.
Wow, so we're really digging into the nitty-gritty details here.
We are, and it's amazing what we can learn from it. By analyzing these jets, we're not just identifying particles, we're reconstructing the fundamental interactions that happen in those proton collisions.
It's like taking a snapshot of the universe a fraction of a second after the Big Bang.
Exactly. And the tools and techniques are constantly evolving. Who knows what other secrets we'll be able to unlock?
Well, that's the beauty of science, right? Always pushing those boundaries, always seeking those answers. It's been incredible taking this deep dive with you, from smashing particles together at nearly the speed of light to analyzing the tiniest details of the resulting jets. It really highlights how far we've come in our understanding of the universe.
It's been a pleasure, and I think it underscores that the most exciting discoveries might still be ahead of us.
Exactly. There's still so much more to explore.